Hello everyone. So in the previous video, we introduced nth order linear ordinary differential equations. Now, what we are going to do in this lecture is actually solve those. And in particular, we're going to solve homogeneous equations, and they are going to be constant coefficient. So again, I'm going to show you that we're getting a characteristic equation. The only issue is that it's going to be potentially higher than quadratic order, and so therefore finding its roots might be a little bit more tedious. But again, let's look at the general setting here. So L of y, this is going to be a0 times the nth derivative plus a1 times the n minus first derivative all the way down to an times y. And again, homogeneous equation, I'm going to set it equal to 0 for today. So you know what I'm going to do. I'm going to set y equal to e to the rt. And then this gives me that when I put this into L, well, e to the rt, this reproduces itself under differentiation. And essentially, I'm going to get a naught r to the n plus a1 r to the n minus 1 all the way down to an, and then e to the rt is equal to 0. And so, just like what we had before, we get a characteristic equation. And that is, of course, solving this polynomial equal to 0. Now, where that comes from is that the only way that this thing can equal to 0 for all time, since this is not equal to 0, then we have to satisfy this equation. So a0 r to the n plus a1 r to the n minus 1 all the way down is equal to 0. So again, the problem boils down to finding roots of a polynomial. Okay, so let's just do some examples. We're going to ride through the rest of this lecture with a ton of examples. We might even have to remind ourselves how to do a little bit of factoring of high degree polynomials. Let's take a look at one right off the bat. It's going to be a fourth order linear differential equation. So the fourth derivative plus the third derivative minus 7 times the second derivative minus the first derivative, and then plus 6 times the function itself. Okay, let's throw in some initial conditions as well. Y of 0 is equal to 1. Y prime of 0 is equal to 0. Y double prime of 0 is equal to minus 2. And this is a fourth order equation. I need 4 initial conditions. 1, 2, 3, 4. And let's put this equal to minus 1. Okay, now let's go ahead and let's solve this thing. So first off, what is the characteristic equation? So characteristic equation, well, putting in e to the rt into this thing gives me r to the 4 plus r cubed minus 7r squared minus r plus 6 is equal to 0. Now, you might remember how to solve these things. Typically, you have to sort of do a little bit of a guess and figure out what a potential root is. In this case, actually, r equal to 1 is a root. You get 1 to the 4 plus 1 to the 3 minus 7 times 1 minus 1 plus 6. So that's plus 8 minus 8. That's equal to 0. Now, here's something you probably dreaded, and unfortunately, we're going to have to use it again, but that is long division of polynomials. Now, this is not unfortunate for me because I love long division of polynomials, but let's do this. R equal to 1 is a root. Okay. Let's divide r minus 1 out of this thing, right? We're going to factor it. So I get r to the 4 plus r cubed minus 7r squared minus r plus 6. Now, what do I need to multiply r to get r cubed, or r to the 4? That is an r cubed. So then multiplying this whole thing by r cubed, r to the 4 minus r cubed. Subtract these two things, I get 2r cubed minus 7r squared minus r plus 6. Then, now this is my new polynomial. What do I need to multiply into the r to get 2r cubed? Well, that's plus 2r squared. And so now I get 2r cubed minus 2r squared. And doing the subtraction here now, minus 5r squared minus r plus 6. Same thing, what do I need to multiply into r to get minus 5r squared? That's minus 5r. Minus 5r squared plus 5r. Now I get minus 6r plus 6. And in this case, I multiply in minus 1. Minus 6r plus 6. I did it correctly. There's no remainder. And so now, all of this together, maybe I'll sort of sneak it in right here just to save a little bit of space. But now my characteristic equation becomes r minus 1. That's what I factored out. And then r cubed plus 2r squared minus 5r minus 1 is equal to 0. Okay, now you can play the same game. I'm going to go ahead and sort of skip through this. I'm going to tell you what the rest of the roots are, just for the sake of brevity, okay? So you can use whatever method you want. You just have to factor that cubic now. But in this case, the roots are, well, r is equal to plus or minus 1. Plus 1 we already found. Minus 1, 2, and minus 3. And so therefore, y of t is equal to c1 e, and then to the t, that's the plus 1 root, plus c2 e to the minus t, and then plus c3 e to the 2t, and then plus c4 e to the minus 3t. All right, so 4 solutions, each one coming from a real root of this equation. And we add them together using the principle of superposition. So same basic idea from last time. And now if I want to satisfy my initial conditions, well, let's take a look at it. Initial conditions. Okay, well, my first initial condition is 1. So I get 1 is equal to, now putting t equal to 0 here gives c1 plus c2 plus c3 plus c4. Similarly, taking a derivative and setting that, or evaluating that at t equal to 0 gives 0 from my initial condition is equal to c1 minus c2 and then plus 2c3 minus 3c4. Again, that's just coming from the derivative of this thing and evaluated at t equal to 0. Second derivative. So you can see that this is getting tedious quickly, right? Not only does it involve factoring a high degree polynomial, but it's also going to involve solving for 4 unknowns. So it's getting more complex in the sort of function side or the polynomial side, but also more complex in the linear algebra side. So I get c1 plus c2 plus 4c3 and then plus 9c4. And then the last one, minus 1 is equal to, okay, so I get c1 minus c2. So again, just taking the third derivative, evaluating at t equal to 0, and you get this big, ugly equation. Now, it's up to you how you want to solve this. You can use row reduction to put this in row echelon form. You can just put it into a solver, Mathematica, Maple, anything like that will do the trick. Wolfram Alpha, for example. It is entirely up to you. I'm going to go ahead and give you the solution, mostly because I'm more interested in what this says about the solution. I'm less interested in doing these rote calculations that you should be quite good at by now. So C1 gives you 11 over 8. C2 gives you 5 over 12. C3 gives you minus 2 over 3. And C4 gives you minus 1 over 8. And so therefore, you can put all this together. Y of t is equal to 11 over 8 e to the t plus 5 over 12 e to the minus t minus 2 over 3 e to the 2t and then minus 1 over 8 e to the minus 3t. Here it is. There's my solution, right? So again, it doesn't really involve a whole lot of calculus. Mostly finding roots to equations. Okay, it's a bit of a pain. It might require a little bit of long division. We can handle it. Or then using a little bit of linear algebra. So these are all sort of introductory concepts in a mathematics curriculum. So this is, technically something that could be handled. Let's keep rolling. Let's do another little quick one here while we have a little bit of board space left. Fourth derivative of y minus y itself is equal to 0. Okay, characteristic equation right off the bat. R to the 4 minus 1 is equal to 0. So in this case, this gives me r squared is equal to plus or minus 1, right, after taking one square root. And then taking the square root of the positive 1 gives me r is equal to, again, plus or minus 1. Taking the square root of the negative 1 gives me plus or minus I. So I have 4 roots, 2 real, plus or minus 1, 2 imaginary, plus or minus I. So what is the general solution here? Just like before. Right, so we have all of this knowledge that we built up when we were doing second order equations. Don't forget it. Carry it over. So we got cos of t plus c4 sine of t, right? So the only thing that we're seeing that's really different is more terms in here. Nothing more than that. Now I get a nice general solution. It mixes exponentials and cosines and sines. Right? That's something that we didn't see that could happen with second order equations, but this just comes from the fact that roots can be, you can have complex pairs, but you can still have real roots to higher order polynomials. Okay, let's take a look at another example. So this is going to be a fun one. I can feel it. Let's see. Fourth derivative plus 2 times the second derivative and then plus the function itself is equal to 0. We're going to drop the initial conditions because we're really just going to sort of work through what the solutions to these look like. Well, let's take a look at this. Characteristic equation. Characteristic equation gives r to the 4 plus 2r squared plus 1 is equal to 0. Well, this is actually an expansion of a square. This is the same as r squared plus 1 all squared is equal to 0, which gives us that we have a double root. So r equal to, now solving this thing, r squared plus 1 equal to 0. It's plus or minus I. And in this case, they're both double roots. So from the fact that these are single roots, I've got y of t is equal to c1 cos of t plus c2 sine of t. That's coming from the plus or minus I being solutions. But now these are double roots. We know what to do with repeated roots. We saw this back when we did this with second order equations. It's just a reduction of order that can be used to derive these solutions. I'm going to go ahead. We're going to use some intuition. C3t cos of t plus C4t sine of t, right? And that's just coming from the fact that we have repeated or double roots at plus or minus I. One of them leads to a t in front of the cosine. One of them leads to a t in front of the sine. This is just like what we saw with the resonances before. It's all the same type of ideas. Okay, let's take a look at one last example. So this is going to be a little bit more exciting, I think. We're going to work with another fourth order equation. Fourth order plus y is equal to 0. Now, we've seen we saw that when that's the second derivative plus y, you get sine and cosine. So the question is, what do I get now when I have a fourth order plus y is equal to 0? Well, the characteristic equation becomes the fourth, r to the fourth plus 1 is equal to 0, which is the same as saying r to the 4 is equal to minus 1, which is the same as just saying r is equal to the fourth root of minus 1. Now, remember, we need 4 different roots to this equation. So how do we solve this? Well, we're going to have to use a little bit of complex numbers here, or a little bit of complex analysis. So let's remember something. Remember Euler's identity? So let's recall e to the I pi is equal to minus 1. Right? So that is coming from Euler's formula. E to the I theta is equal to cos theta plus I sine theta. Then, when you put in pi for theta, the sine term disappears. There's no imaginary part. But cos of pi is minus 1. So e to the I pi is equal to minus 1. Also, remember, this is just sines and cosines in disguise. This is the same as saying e to the I pi and then plus I 2 pi m is equal to minus 1 for all integers m. Why? Because the 2 pi m is just going backwards or forwards an entire period. Actually, it's going backwards or forwards m periods, right? This is just the periodicity of sines and cosines. So technically, this exponential with just a complex exponent is a periodic function, right? I can just keep adding I 2 pi m to the exponent there and keep getting the same number. And again, that just comes from the fact that Euler tells us, so maybe we should just write this below, this is cos of pi plus I sine of pi. And those two things we recognize as being periodic functions. Okay, so how does this help us? Well, let's put in, for this minus 1 here, let's put this thing in. So I get r is equal to e to the I, and now let's factor all of this together, pi plus 2 pi m. Now this works for every single value of m, and then to the 1/4. Okay, let's simplify it a little bit. R is equal to, now I'm going to get e to the I, and then pi over 4. So I'm just multiplying the exponent in, exponent to an exponent. That just means we multiply them. And then plus pi times m over 2. And again, this holds for all m and z. Now, we went from what looked like just one solution to infinitely many, right? There's one for every single value of m. So what happened? Well, let's actually start enumerating some of these solutions in terms of different values of m. And then let's see what happens here. So m equal to 0. This gives me r is equal to e to the I pi over 4. Right? This term disappears. And if you want to, you can put this into the cosine and sines. So this is cos of pi over 4. That's equal to 1 over the square root of 2. And then plus I sine of pi over 4, which is again equal to 1 over the square root of 2. Right? So pi over 4 is the value where sine and cosine are actually equal to each other. Okay, this is okay. I can do this. Right? It's just remembering some values of trig, but that's okay. Now, if m is equal to 1, I get pi over 4 plus pi over 2. So I get e to the I 3 pi over 4. Now, I just need to put this into cosine and sine. So cos of 3 pi over 4, that's minus 1 over the square root of 2. And putting that into sine, I get, again, I over the square root of 2. So I got two different roots, right? They have the same imaginary part, but they have different real part. All right, let's keep having fun. M equal to 2. Well, in this case, I'm adding pi here. So this becomes e to the I 5 pi over 4, which now gives me cos of 5 pi over 4 is minus 1 over the square root of 2. And sine of 5 pi over 4 is minus 1 over the square root of 2. So again, they're equal to each other at cosine and sine are equal to each other at 5 pi over 4 as well. It's just minus 1 over the square root of 2. Okay, I got 3 roots. I should be able to guess that I need 4. So let's keep going. Let's see if we get another value. M equal to 3. Then I'm adding 3 pi over 2 to this thing. And so I get e to the I 7 pi over 4. In this case, evaluating cosine at 7 pi over 4 is 1 over the square root of 2. And sine at 7 pi over 4 is negative 1 over the square root of 2. 4 different roots, all given by plus or minus 1 over the square root of 2 plus or minus I over the square root of 2. Okay, so then what happens if I keep going? Well, m equal to 4. In this case, I get 2 pi. So I'm adding 2 pi. So I get r is equal to I. So let's take a look at this. Plus 2 pi. But this is just pi over 2, or sorry, pi over 4, which is this root right here. Same thing, if I use m equal to 5, I'm just going to get this root by periodicity. If I use m equal to minus 1, I'm just going to get this root by periodicity. So all I need to do is enumerate 4 values of m starting from 0. And these give me my 4 distinct roots in the complex numbers to this equation. In fact, they gave me the 4 different fourth roots of the minus 1 term. So this is how we would solve this, right? I could replace this with a 1 over 6. You could do the same thing, right? Running it up, you could get 6 different solutions here. Okay, so now let's put it all together. Y of t is equal to, okay, what do my solutions look like? Well, 2 of them, so they're coming as complex conjugate pairs. 2 of them have positive real parts. That's given by e. And then this is 1 over the square root of 2. So it's t over the square root of 2. And then cosine. And its imaginary part is, again, 1 over the square root of 2. So I get t over root 2. Its complex conjugate gives the sine term. So t over the square root of 2, sine of t over the square root of 2. Okay, so which ones are those? That was this one and this one. That's complex conjugates. 2 more to go. C3, e to the minus t over the square root of 2, cos t over root 2. And then plus C4, e to the minus t over root 2, sine of t over root 2. And that is these two right here. That is the solutions. Okay, so now we've seen something slightly new potentially, and that is how we find roots in the complex plane, right? So this is the fourth root of -1. We had to get exactly 4 roots. We had to use Euler's identity in order to find that thing, right? So this is really the sort of bulk of the problem, is finding what these roots are, but you could do this for a variety of problems, right? I could make this equal to 2 here. You could do the same thing. I could make that r to the 5. I can make it r to the 10. You can still do it, right? If it's r to the 10, there's going to be 10 different solutions. You're going to go m equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then after that, it'll start repeating. Same basic idea. Some of them might be more tedious than others, but it's just using what we understand about complex numbers, and in particular the relationship by exponentials raised to a complex, purely complex power, how that relates to sine and cosine functions.